Hi students. So we've learned arithmetic sequences and arithmetic series. We've also gone through geometric sequences, and now we're going to understand geometric series. To be able to understand geometric series first, it's also very important for us to just recapitulate what geometric sequences are. We do know that the geometric sequences are having a common ratio, and therefore you can find the nth term of the geometric sequence as given there here on my screen, which is un is equal to u1 r to the power of n minus 1, where we know that u1 is our first term and r is our common ratio. Now, as you have a formula to calculate the sum of arithmetic series, similarly, you do have a formula to calculate the sum of geometric sequences or geometric series in that case. So how do we go about it, and how does this formula come about? So let's go ahead and have a look at that. So we do know that we've already found out that this is our u1, un is equal to u1 r to the power of n minus 1. Now I'm just going to go ahead and use this tool, and yes. So if I want to go ahead and find out the sum, so I will go ahead and write Sn is equal to, so the first term in terms of our nth term of a geometric sequence, which we already know, will be, if it's the first term, it's going to be u1, right? Because when I say n is 1, then 1 minus 1 is going to be 0. So out of the power of 0 is 1. Therefore, the first term would become u1. Then the second term. So when I substitute n is equal to 2, then I am going to have my term in the form of u1 into r. When n is equal to 3, you will have your expression as u1 r to the power of 2. And similarly, as we go on, this will continue to the point where we say that the last term, or the second last term here in this case, would be u1 r to the power of n minus 2 plus u1 r to the power of n minus 1. So here, that's when I say that that's the nth term, that's the last term of the series. Now, if I just go ahead and multiply the entire equation here that I have with r, so I'm going to just multiply by r. Now, if I do this, then I am going to get r Sn is equal to u1r plus u1r square plus u1r cube plus, so it goes on, and then the second last term will become u1r n minus 1 plus u1r to the power of n, right? Now, if I just go ahead and assume that this is this one and this one, these are two equations that I have. This is my first equation and this is my second equation. Now I'm going to use these two equations and try to see if I do some manipulation and I get my formula. So if I go ahead and subtract the first equation from the second equation, and if I do this, I will get Rsn minus Sn is equal to, everything will get cancelled except the last term here and the first term. Okay, let me go there. Yes, and the first term here. Okay, so when I write this down, it is going to be u1 r to the power of n minus u1, right? Now if I just go ahead and simplify this further and see if I can factorize something, I do see that Sn is common and r minus 1 can be written in bracket. U is equal to, again I see u1 can be taken out as common, so u1 r to the power of n minus 1. All right. Then if I just go ahead and continue solving this, Sn, I see r minus 1 can be taken to the other side. So you have u1 r to the power of n minus 1 to the power, divided by r minus 1. Now this is our formula to calculate the sum of a geometric series. All right. So the formula that we have here right now, of course, we need to remember that this formula is only and only applicable when r is not equal to 1, because if r is equal to 1, then we do understand that the denominator is going to become 0, and therefore this is not possible. You will not have a geometric series in place. So it's very important to understand the condition at which this formula is applicable. There's also one more extension that we can actually go ahead and do, and if we just go ahead and modify this, we will see that we can also write this particular formula as Sn is equal to u1 1 minus r to the power of n over 1 minus r. Now the formula remains exactly the same. There is not much of a difference here, and you will get the same answers irrespective of whichever formula you use. However, for our convenience, what we do is when our r, let me just use a highlighter to kind of give you an understanding. So here we go. Yes. So when our r is less than 1, all right, when our r is less than 1, it's easier to go ahead and use this one, right, this formula, because in that case you're not going to get negative values in the denominator, and yes, the calculation becomes easier. When r is greater than 1, then it's easier to use this formula. Therefore, again, for the convenience of our calculation, irrespective of whichever formula you use, you will get the same answer. All right, so this is very important for you to know. Let's proceed with one question now and just take an example and see if we've understood this. So the question given here is, find the exact value of the sum of the 6 terms of the geometric sequence with u1 is equal to 8 and common ratio is given us as 1 over 2. Now I would want you to just pause this video so that you can go ahead and solve it. Once you've solved it, then come back and we'll check out the solution here. So since r is less than 1, I've taken the formula where I am going to use 1 minus r in the denominator and correspondingly 1 minus r to the power of n in the numerator. I've just gone ahead and substituted the values, the information that's been given to us. So S6 is equal to 8 into 1 minus 1 by 2 to the power of 6 by 1 minus 1 by 2. When we go ahead and solve this, we are going to get, here we go, yes. So when we go ahead and solve this, it's going to be 8 into 1 minus 1 over 64 over 1 by 2. And then, yes, when we go ahead and further solve this, the answer that we are going to get is 16, because 2 comes over to the numerator. So 2 times 8 is 16. 1 minus 1 over 64 is going to give you 63 over 64, and therefore the final answer is 63 over 4. Please do remember the key term that's been given to us very, very clearly, and that is something we should remember, is that it mentions it's an exact value. They are asking you to write your answer in terms of an exact value, and therefore my answer should not be written as a decimal. It should only and only be in terms of a fraction or a whole number. That's the difference between your final answer written as an exact value or as a decimal, or in terms of within an approximated value. All right. Now, let's go ahead and move on to geometric series in terms of certain interesting things that we're going to look at when there is some changes in terms of the value of r. So in the previous video that you had seen on arithmetic series, Mr. Ganesh had clearly mentioned about how we do have something called as infinite series. And we talk about infinite series as a set of series where the terms continue to go ahead. Now, when we are looking at these and we go ahead and add these together in an arithmetic sequence, the sum of these arithmetic series will go ahead and keep on adding, and they will increase without any limit. When these kind of sequences increase without a limit, they are called as divergent series. So I'm just going to go ahead and write this. This is an important keyword that you need to know. When we are talking about normal sequences that go ahead and continue to increase the sum, the total sum continues to increase when you keep on adding the number of terms of these sequences, then these sequences are behaving normally and they're called as divergent series. However, in geometric series, while you do have a lot of geometric series that behave divergently, you do have a certain section of geometric series that do not conform to this pattern. So you do see that there are certain set of geometric series that will not continue to increase the sum. However, they come closer and closer and closer to a certain value as their total. And when this happens, we say that these kind of geometric series are nothing but convergent series. They are converging. Their sum is converging to a particular value, and therefore they are called as convergent series. Now we're going to today take an example and actually see how this behaves graphically to be able to have more clarity of understanding here. So here in the GeoGebra tool that we actually see, we are seeing on the x-axis the terms and the corresponding sum as you keep on increasing the number of terms in this series. All right. Now at the moment I have kept the maximum number of terms for me to get the sum of the series is 20. So 20 terms here. All right. I start with n is equal to 1, and here it's calculating directly. All right. The value, the sum you're going to be seeing here. So when we are looking at n is equal to 1, and I'm going to go ahead and also trace the point. I want to see where exactly the sum is at each term. All right. So I'm going to do that, and as I move from n is equal to 1 to n is equal to 20, I do see that there is a consistent value that is coming closer and closer to. Now that is something you need to see and understand. Let me just go ahead and now change this maximum number of terms to, let's say, 1000. Okay. Now if I do this, all right, now let's see how this is going to behave. So from 21, if I just say I am going to go ahead and plot 100 values, it's coming closer. It has become from 0.95, it has become 0.99. Then I move, let's say, to more than 500 values. It's coming more closer, and it's now 0.9983. As I move on towards 800 values, 0.9988. If you see, it is coming closer and closer to, yes, you guessed it right, it's coming closer and closer to 1, right? When I come to 1000 values, it's coming 0.999. However, it does